is obtained using sine rule. 20 over sine B equals to 58 over sine 150. Sine B, by collecting like times sine B, is equal to 20 sine 150 all over 58, which will give us 0.1724. Getting the sine inverse when sine is crossing over, it becomes sine inverse of 0.1724. We have 9.93 degrees of the reaction. Example 6. Figure 135 example shows a parallelogram having two sides of 10 Newton, having the diagonal at an angle of 60 degrees and the angle of the side of the parallelogram as 120 degrees. Find the resultant F in figure 135 above. Solution. Using cosine rule, F squared, capital F squared is equal to capital Q squared plus capital P squared plus 2QP cos theta, where theta is the angle between the forces P and Q. Theta is equal to 60 degrees, Q is equal to 10 Newton, P equal to 5 Newton, F is unknown. So, substituting the values, we have F squared is equal to 10 squared plus 5 squared plus 2 times 10 times 5 cos 60. F squared is equal to 100 plus 25 plus 100 times 1 over 2. F squared is equal to 100 plus 25 plus 50 is equal to 175. F is equal to the square root of 175, which gives us 13.23 Newton. Direction of F tan alpha equal to, in bracket, P sin theta all over, in bracket, Q plus P sin theta, where alpha is equal to direction of force F. Therefore, tan alpha is equal to, in bracket, 5 sin 60 by substituting the values, all over 10 plus 5 sin 60. Alpha is equal to tan inverse of 0.30217. Alpha is now equal to 16.8 degrees. Example 7. If a force P of 40 Newton acts in direction due east and another force Q of 30 Newton acts in the direction due north, calculate the resultant of these two forces. Q at due north 30 Newton, while P at due east 40 Newton. We have to get the resultant R. We have that from Pythagoras theory, the square root of the hypotenuse is equal to the sum of the squares of the other two sides. R squared is equal to P squared plus Q squared. R squared is equal to 40 squared plus 30 squared, which is equal to 2,500. R becomes square crossing over will become square root of 2,500, which is 50 Newton. Also, tan theta from trigonometry, law of trigonometry, is equal to 30 over 40, which is 0.75. That is theta. Tan inverse of 0.75 is 36.9 degrees. Therefore, the resultant is 50 Newton, makes 36.9 degrees with 40 Newton force. Triangular forces. This states that if three forces are in equilibrium, they can be represented in magnitude and direction by the three sides of a triangle taken in order. Suppose x, y are the representative algorithm sum of the resolved components in two perpendicular directions of three forces P, S, T in equilibrium. Figure 137. Then, since SY can each be represented by the sides of a triangle drawn to scale, the resultant R is given by R squared equals S squared plus Y squared. Figure 237 shows the resolution of forces at a point. Example 8. Three strings are attached to a small metal ring. Two of these rings makes an angle of 35 degrees with the vertical, and each is pulled with a force of 7 Newton. What force must be applied T, the third string, to keep the string stationary? Solution. Looking at the diagram, the body is hung by a string 7 Newton at an angle 35 at the left, 35 at the right each, to suspend a body T of resultant. So we can represent the forces on a triangle. If the left hand side of the force resolved is 35 degrees is put on the first coordinate at a point B, then the second coordinate will be at point C, which is for the right hand side of the force resolved. Then the resultant, or which the two forces are carrying, will be AB, which is the T we are looking for. Since the string is in equilibrium, we use triangle of forces. Use Lenz's theorem. T over sine 110 degree equal to 7 over sine 35. Therefore, making T the subject of the formula, we have, and putting in the values, the unknown values, we have in bracket 7 sine 70 degrees all over sine 35 degrees is equal to 11.4547 Newton. Note, the condition for the equilibrium of three non-parallel coplanar forces are: the line of action of the force must meet at a point, the algebraic sum of forces at a point must be equal to 0, all the three forces must be coherent. Example 9. Figure 1.39. Three forces. In figure 1.39, three forces F1, F2, and F3 acting at O in equilibrium. If the magnitude of F1 is 10 Newton and the magnitude of F2 is 5 Newton, calculate the magnitude of F3. If knowing that F1 and F2 are at an angle of 60